I am going to pass control over to Brandon, and he's going to kick things off.
Awesome. Thanks a lot, Adam, Andrew over there at BoltSource. Excited to be part of GraphQL Texas here today. I'll go ahead and share my screen and get started. So my name is Brandon Valosek. I am a software engineer at Yonomi. It's a smart home startup based out of Austin, Texas and Boulder, Colorado. Super pumped to be here for the second GraphQL Texas event. Looking forward to hearing from some of the other speakers today, Adam and Anthony, later on. So with that, let's go ahead and get started. The name of my talk is GraphQL, the architecture behind the graph, or how embracing GraphQL can enable exciting platform architectures. So this will be a fairly high-level discussion for a general tech audience. I'm assuming that you have a general idea of how GraphQL works. Maybe you played around with it a little bit in the past. I'm not going to go super deep into any code or any of the nitty-gritty implementation details. Happy to go into any of those details during the Q&A session if you want to get down to the nuts and bolts of how it all works. But primarily looking at the high-level architectural components around a lot of the stuff with GraphQL. So maybe you have a monolith and you're thinking about cracking it open and making it into more of a microservice-based architecture. Maybe you played around with GraphQL a little bit in the past, or maybe you're using it right now and it's starting to get a little painful over time. So if any of those things apply to you, this will definitely be a good talk for you. If you're super fluent already in microservice architectures, distributed architectures, event-based architectures, a lot of this will be familiar, but doesn't hurt for a refresher. So a little bit of context and scope of what I'll be talking about today. GraphQL is an API paradigm and platform and convention. I won't be talking about the client side at all. I won't be talking about mobile apps or web apps or anything that's communicating with a GraphQL API, but rather I will be looking at what happens when you adopt a GraphQL API and how does that change the way you can think about the way you implement and architect and build the platform that is powering that graph. So we'll start out with a quick little bit about me. I'll be going into something I call letting go of the canonical data model. This is introducing a different way of thinking about how we model our data that plays well with GraphQL. And it's a little bit of a departure from how you might be used to thinking if you built traditional kind of monolithic CRUD apps. I'll be talking about leaning into distributed architecture. What should our idealized architecture look like, or what should we strive for when we're building a cloud platform that has a GraphQL API in front of it? Also, GraphQL is pretty complex and pretty challenging. Being aware of the challenges and pitfalls and where some of the really hard tech problems tend to pop up is an important part as well when you're building a GraphQL platform. So I'll be going into that. And then I'll be wrapping it up with kind of my overall thoughts on all of that. So about me, like it was already mentioned, I'm a software engineer at Yonomi. Yonomi is a simple smart home integration platform. We make it easy to build killer experiences for the smart home. It's interesting because our product really is, in a lot of ways, the API, basically. So that makes something like GraphQL, or just thinking critically generally about the product that is our API, a really important part of how we think about our business, basically. I'm a full stack cloud platform engineer. What that means for me is that I've been in charge of designing, architecting, and implementing cloud platforms kind of from end to end. So that does include some front end stuff as well as back end, but also just having a say and being involved in all parts of the stack from end to end. I was a GraphQL skeptic. Originally, when I first heard about it years ago, I immediately saw the client-side benefits of being able to select the specific data that you wanted, all of the really great developer ergonomics around GraphQL on the client side. But I was very concerned about what a platform might actually look like if you're trying to build one of these things out. So eventually that came around, and obviously now I'm a big GraphQL fan, and hopefully I can maybe sway a few skeptics here today as well. Some stuff that I really like as of late, of course, GraphQL, TypeScript. I'm a huge fan of static typing, serverless stuff, especially with AWS Lambda, huge fan there as well. Microservices and distributed architecture. Those are the things lately that I've been super interested in. So let's talk about embracing the graph and what that means. The first thing that I want to talk about is this notion of letting go of the canonical data model, or getting us to stop thinking in this notion of bloated models and instead start thinking about composite entities. So I'll go into specifically what each of those means and kind of the differences between them, and really how the latter really is the kind of the approach you want to take when you're really leaning into GraphQL overall. Again, if you're already pretty familiar with and fluent with distributed architectures and kind of this very large microservice approach at scale, this should be pretty familiar to you. So what is the canonical data model? This is just a fancy word, really, of saying the one model that we use all over the place. So it is the user model, the post model, the device model, something like that. It's independent from any specific service or context because it is just isolated in its own little sense and used by multiple services. The idea behind this is that it's supposed to reduce dependencies and transform logic because there's the one way that everyone talks about these various pieces of your application's data, which sounds great, but the reality is at scale that tends to break down. So yes, it's great that we have this one single way of talking about things. Maybe it's simpler, but it ends up tightly coupling the services, the domains, our code bases to this specific one model. Over time, this leads to bloated tech debt. These models become a dumping ground as you add more and more features. You eventually get to the point where you have this very brittle, scary velocity black hole of a gigantic model because you have all these different separate code bases and services talking about and operating on some of the same sets of assumptions. So over time, eventually you'll just have all this stuff build up. And it becomes a velocity black hole. And what I mean by that is developers and teams become scared of messing with this too fast or changing it too dramatically because they risk breaking something that is dependent on this gigantic model because they're not aware of exactly what's going on with it. It's difficult and impossible to tell, really, of what parts of your platform kind of depend on that concept. So an example of a canonical data model, a simple one in this case, is we'll go with a device. In our case, a smart light bulb. This is very relevant to us here at Yonomi with all the smart home stuff that we like to do. A bulb is very simple, can be powered on or off, can be dimmed. And let's just throw up a sketch of what this model might look like. Now, obviously, this is a very simple, tiny example. In real life, anyone who plays with enough REST interfaces knows that these responses get gigantic, and over time, this is the canonical data model that kind of builds up and gets large, right? But looking at the pieces of information we have here, we have basic stuff like an ID, an owner ID to represent the user who owns this device, whether or not it's enabled, it's connected, other information like how the device is actually configured, as well as things like the current state of the device. So this could be some properties reflecting what's going on at the device at that time. Now, if you'll notice, there are several different concerns all mixed in with this model. We have configuration information that's involved the life cycle of the device as it comes into our cloud. We have state information. This could be highly transient. This could be some event-based stuff that we're reading in. It could be part of transactional data as another part of our system. And we have connectivity information. So this would depend on the nature by which this device came into our system. Is it online? Is it connected to our IoT gateway? Are we aware that this device is currently working with the third-party vendor? So there's a lot of stuff that we've basically packed into there. It's not bad that we have all that, but anyone who's trying to interact with this device now has to be aware of all of these pieces and potentially can start depending on these pieces, which will slowly begin to couple all the pieces of your system over time, which can be a scary thing. So a canonical data model can quickly become an iteration bottleneck as it bloats over time and ends up tightly coupling the pieces of your system. The alternative to this, or what I would present as an alternative to this, is the notion of composite entities. So this is an alternative way of thinking about how things are represented throughout our system. An entity is really just an abstract identity. It is the device, it is the user, but that's all it really is. Beyond that, we want to kind of focus on the different domains that care about this specific entity. This could be things like your microservices, or even more broadly, like your business units. So for instance, a user that is kind of managed by a social service is aware of things like your friends and other stuff like that. But a user that is managed by your payment service is aware of things like your credit card information and maybe payment details and things like that. Each specific domain or business concern will have a different way of thinking about and representing information about these entities in their system. So domains are only concerned with their own data. We don't want to burden these individual chunks of business logic or services with a bunch of information that they don't need. And specifically, we want them to be in charge of their own data as well. We can rely on gateways, and this is where the GraphQL piece is finally coming in here, to compose these assembled views of these kind of disparate components that we have here. So what I mean by that is we have these individual domains that have different ways of talking about the same thing. So you have the user that can be talked about from a payments perspective or from a social perspective or even a profile perspective, how they configure their user. We want something in front of all of these things, or a gateway or GraphQL API in our case, to be able to assemble a view that is a composite version of what all that looks like. What's great about this is we can get rid of cross-domain dependencies. We can let each chunk of the business logic or each service focus specifically on what they need to operate and the information that they're aware of and is relevant to their specific domain without having to leak information throughout all the other parts of the system. What's interesting with this is we no longer have a single source of truth for what our entity actually is. We don't have that canonical data model. Now, this is the whole point, and that's okay. And this distributed notion of truth is actually a really important part of building distributed web applications at scale. You forego the ability to have a perfect and accurate comprehensive snapshot of what your entity data actually is, but that's okay because in reality, the truth is actually really distributed as well. A single entity can be thought of in various different ways across the platform overall. So what does this look like in practice? Let's go back to the smart light bulb example that I showed earlier with the canonical data model. If we kind of break down the concerns that we were looking at there, the various parts of that model that actually make sense, we looked at the configuration of the device, some various properties around that. We looked at the connectivity information, whether or not it's online or not. And we also looked at the device's state. This is the information about its current properties and what it's looking like in real life. If we take that canonical data model and slice and dice it across some of these things, what we end up with is three smaller, very focused models here. You'll notice that in the device configuration, I simply just have the relevant information there. Same for the IoT side as well as the state side. Each of these models has the same ID. That is really the correlating factor that is able to tie all these different projections of this information together in the same sort of way. But each individual service just has the information that it needs. The state service doesn't necessarily have to care about whether or not the IoT connectivity is currently enabled or when the last activity was there. It's really just concerned about the state. Same with the device configuration. Device configuration is separate from the way that's able to come online within our cloud. And so we don't need to couple that information if we don't have to. You'll notice that there's an enabled true flag there. For all of these services, that's okay. In real life, you'll often have information about your entity that is relevant across all of these different domains. The way that's actually handled on the implementation side is really about embracing more of an event-based architecture, which I'll talk about in a little bit. So composite entities allow you to let each domain dictate the best way to represent a thing within their own local context. Now, GraphQL, which is what this is all about. These composite entities that I talked about, these sort of these split apart representations of an abstract thing that you care about in your platform, we need to surface these composite entities as GraphQL types within our graph. If you look here on the right side, you'll see that I have a basic mocked up query that I have here of asking for a specific device by its ID. And you'll notice that I'm asking for all the information that we've been talking about that's here in our system. GraphQL allows you to write query resolvers to answer a query, and that's very much so like an RPC style, just answering a single response. You can do a little bit better than that and build type-based resolvers, where you're resolving the entire type all by itself. So every time you resolve a device, say, out of your graph, it's resolved the same way. But most GraphQL server implementations also allow you to go even further, more granular than that. You can actually resolve things on a per field basis, which is great for us because we've started breaking out these composite entities into specific fields that we care about from different services. So what I mean by that is if you look at the model that we have here and you look at this query that exists, we have all this information coming from these different services that we've been walking through here. A single graph type, in this case, our device type, is resolved from multiple sources in our backing platform. So the first part up here, this is resolved from our configuration service. State and connectivity information are resolved from their respective services as well. The owner ID is also able to come back directly from that configuration service. And what's really interesting is that because we're allowed to kind of nest this information within the graph, we can further query into the subgraphs within the kind of nested model here. So in this case, a device has an owner, which is a user. None of our device services that we talked about in previous slides know anything about how a user actually works. We just have a user ID. It's just a foreign key to a different part of our system. But with the graph, we can allow it to further query into this kind of nested portal deeper within the graph and ask additional services. In this case, let's just say the user service, for more information about that context that's there, which is great. So GraphQL lets us embrace the scalability of distributed truth with the convenience of a single unified API view. So that was the case for embracing the notion of composite entities. That was the case for really relying on truth being more of a distributed thing rather than a single canonical model that we're able to rely on. What I want to talk about next in embracing the graph is what does it look like to lean into the distributed architecture patterns that are required to really build something like this to make it actually work. Primarily, I'll be looking at what it means to build tiny microservices, as well as favoring additive innovation over refactoring. So just to make sure we're all on the same page, when I say microservice architecture, this is just the first image that came up when I Googled it. And the idea generally is you have clients that connect to an API gateway. In our case, it's going to be GraphQL. This API gateway is able to delegate requests to a handful of microservices that are on your platform. Each microservice is fully independent. It's got its own backing data store. It could be a different database, could connect to third-party services. They each are their own little tiny service in their own little world. So that's Microservices 101, if anyone wasn't familiar with it. Anytime we talk about distributed architecture, it's great to bring up Conway's law, which says any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. That was from Melvin Conway in 1967. The way I like to think about this is if our software team structure can more closely mimic the platform architecture, we can iterate in a much more natural and intuitive way. So what does it really mean to lean into this distributed architecture overall? We have these composite entities that I've talked about. We can stitch these together via the graph side joins, really, which is what I talked about in the previous slides. You have all of these services that have various information about your specific entities. We can rely on the really cool tech and things like Apollo server and other GraphQL server implementations to join together all of that data in the presentation layer effectively of our API. Because we can do that, and because the graph allows us to sort of hide the fact that all this information is coming from separate places, we can keep microservices super narrow and super simple. It doesn't matter if it's coming from 5 different places. If the graph kind of stitches it together in a single place, the consumers of our API are able to have a nice, cohesive, and very rich experience. We don't tend to really lose anything or risk much by having a very aggressively narrow approach to how we slice and dice the domains that we build microservices around. We want to fully decouple all of the pieces of our platform as much as we can. In the previous slides, I showed how that enabled true flag was kind of copied around to each of those different domains because that's something that they cared about. Instead of relying on some sort of canonical data model or cross microservice communication, we need to heavily invest into event-based patterns to have this kind of eventually consistent distributed notion of truth. Event-based patterns and event-based architectures are one of the most important things when it comes to building a highly scalable distributed architecture. So this is already something that is probably a core part of your system if you're looking into doing something like this. The platform functionality is presented as a unified graph. So all of this stuff that I'm talking about that is very implementation specific, very engineering team specific, is completely isolated from the effective presentation of your product. And I say product because here at Yonomi, our API really is our product. But even if that's not the case, you are having to present this API to your front-end team or your mobile app development team. We're able to build this great, excellent microservice architecture and hide all that implementation behind the graph in a way that is excellent for API consumers to use and excellent for us to be able to iterate on as an engineering team. So what that looks like from just like a high level perspective, this is a lot like that diagram at the very beginning when I talked about the architecture behind the graph. This is the architecture behind the graph here. We have our API gateway that is running a GraphQL server. Whenever we receive an incoming request from a client, like a mobile app or a web app, that request is broken into several pieces, and that request is delegated down to the underlying microservices that are powering your platform. You'll notice that each one of these services has its own little copy of various pieces of data, all associated with the same ID. This could be things like the device connectivity, its configuration, and its state information, say. Each of those domains really is only aware of those individual pieces, but from our API's perspective, we'd like to present this unified notion of what this actually looks like. Whenever that request comes in, the request for information from the microservices is delegated out to those individual services, and the graph threads it all together for us and presents a nice unified model to the client, to your mobile app or to your web app. Embracing GraphQL really allows us to fully lean into a highly distributed microservice-based architecture. The other thing I brought up that's great about doing this is we're able to iterate rapidly, which is one of the most important things, especially in a software startup, especially in a cutting edge field like smart home and automation. New functionality can be independent from existing work. Whenever we're able to slice and dice things into tiny microservices, and when we can do that without impacting the way that our API feels or the way that our ultimate product works, that is excellent, because engineers can spin up greenfield work really quickly. If you have new features, spin up new services, basically. This way, you're not blocked by existing technical debt or other teams that are working on existing feature sets or anything like that. Platform functionality can come from legacy sources. Now, anyone who's basically been an engineer for long enough knows that all real-life code bases are effectively gigantic Frankenstein monsters. You can draw pretty diagrams of what microservices is supposed to look like, but at the end of the day, it's going to get gross eventually on there. The graph allows us to combine all of this old functionality with the new stuff. We can take legacy sources, maybe that's a crazy monolith, maybe that's some old school application that's still sitting there in your cloud, and we can build alongside that in parallel, brand new greenfield stuff, microservice stuff, go all in with serverless, which is what I like to do, without having to refactor the stuff that's already working. You don't have to refactor technical debt that is already working and doesn't have to change if you don't have to. There's no real intrinsic reason to refactor. This allows us to kind of keep that legacy stuff there and even reproject it in a much nicer way with the graph while still building brand new stuff alongside that. Now, and again, this is a really excellent way of combining what most real life code bases are, which is a very interesting timeline of the tools, technologies, and trends as engineering teams come and go inside of an organization. Over time, we can do what's called strangling the monolith, which is probably a familiar expression to a lot of y'all, to transition all this legacy functionality that I talked about, maybe some of the uglier pieces of that platform, into the newer microservices and newer technologies and things like that. But we can do that over time when it makes sense from a business and roadmap perspective, which is the important part. Strangling the monolith, just to illustrate if anyone isn't super familiar with that, we start over here on the left side with a gigantic old school application, and we want to start bringing in microservices. Maybe you want to throw a graph in front of it and do all the stuff that we've been talking about for this presentation. You start with a large monolith. Over time, you break out pieces of that into a brand new cloud over here, say covered with GraphQL, that has a little bit of that functionality of the monolith broken off into its own standalone microservice. What's great here too is you'll notice throughout this roadmap and this timeline that in addition to paying down our technical debt by breaking off pieces of this monolith, we're able to, in parallel, build brand new features in greenfield environments with new technology and clean code bases. This is all happening in parallel, and it can all be threaded together by GraphQL on the front end as well. So with the help of GraphQL, we can favor rapid innovation and quickly develop new features without getting bogged down with legacy refactors, which in a lot of ways is absolutely the dream. So, did away with the canonical data model, embrace this distributed lifestyle, but it's not always a walk in the park. There are tons of challenges with working with GraphQL, as anyone who's done this for long enough will tell you. So, resolver runtime execution can be complex. That is absolutely an understatement. And anyone that is on my team when we rebuilt the GraphQL server a few months ago can attest to that, because things can get pretty crazy. Now, in a traditional Express or other sort of REST backend server, you can look at your controller code that's handling a request, and you can generally in your head know exactly what's going to happen. You'll make a few calls, maybe you'll do some formatting and some validation, and you're done, basically. The execution pipeline for handling a graph query, especially very complex, very nested, sophisticated queries, can get very gnarly very quickly. It is extraordinarily important to have excellent observability, surfacing instrumentation around query times and hot paths within your resolution stack, more or less, and just really be aware of all the ways that the code base is interacting at the graph level. Now, there's tons of interesting implementation details around things like data loader and some other techniques you can do around batching that really solve a whole lot of these problems, but that's exactly what it is. It's a lot of interesting and complex things that we need to solve for. In addition, schema and resolver patterns have a wide design space. What I mean by that is that there's a whole lot of wiggle room in exactly how you manage and define and iterate on your schemas, where those schemas live in terms of both like the business organization and even the code, and also the way that we actually go about writing our resolvers and how those are coupled to the schema. So that's good to have a large amount of design space. It means that we can be flexible. And here at Unomi, we've definitely pushed some things in some very interesting directions because of that flexibility. But it also means that there's a lot of stuff you'll do that won't work, or directions you'll go that'll end up being pinning yourself into a corner and having to rethink your strategy when it comes to some of this stuff. What's great though is that because this is a solid separation of concerns, that is just our graph. And if we want, we can always scrap it, rewrite it, or heavily iterate on it without worrying about the platform behind us that we're actually surfacing information for. At some point, your graph is going to get extremely big as well. It's going to get very complex. Start wondering if you can then breaking the graph off into smaller pieces and looking at things like federated graphs. So there's a whole lot of stuff if you start pulling on these threads. Other challenges and pitfalls, caching can be challenging. I believe Adam is actually going to be talking about caching later on today. So I'm definitely interested to see what he has to say about that. We don't have network level caching, or at least it's extraordinarily difficult because GraphQL is handled through a single endpoint just using post calls. We can't really benefit from any network level caching on those requests. Query execution can be compute heavy, especially if you're doing large transforms, especially if you're dealing with a huge amount of data. This can get very gnarly very quickly. Now, most of the time you'll be waiting for downstream resources, and so it's not going to be that bad, but it's absolutely something to keep in mind because Apollo server in particular can get very heavy. So again, super important to instrument that, super important to surface those metrics through observability. It's yet another transform layer. That's not bad in my opinion. I think it's great to have very dedicated layers of your application where it has its own specific way of talking about things. You don't want to necessarily surface the technological decisions at your database layer all the way out to your API. In fact, that's almost always going to be a bad idea. You're going to want some way of talking about things at different layers, and you don't want your technology decisions to drive the way your product looks and feels, or the way your API looks and feels. Data type strictness requires clean platform data transfer objects. What I mean by that is GraphQL servers like Apollo server, they have their GraphQL schema and they're very strict about what they surface. If you provide that in your resolvers, a data object that doesn't adhere to the spec of your schema, it is either going to have an error or just throw that data away entirely. It's very important that the information that your graph is receiving from the rest of your platform is very well understood or validated, or statically typed is the best way to go about doing that as well. That's a subtle TypeScript plug, by the way. At the end of the day, we're still going to need non-graph endpoints. We have things like file uploads, high volume ingestion, OAuth flows, other standardized APIs. It is not always going to be the best solution, and trying to shoehorn in stuff into the graph that doesn't belong is going to get painful very quickly. So not great that we have this excellent graph that we can do so much cool stuff with, except for a few other things that we can't do with the graph. So ultimately, GraphQL is complex. It requires sophisticated implementation at scale, but competent teams can mitigate the largest of these challenges and really reap the benefits. So to wrap it all up, you let go of the canonical data model. You embrace this notion that truth is really distributed at scale, and you slice and dice your models to the narrowest domain-specific ways that you can. You avoid coupling your domains together, and you break down the data into manageable, understandable chunks. We lean into a distributed architecture, focus on building these microservices around narrow domains, rely on the graph to thread all this information into a cohesive view, and benefit from patterns like strangling the monolith to slowly and iteratively move our platform into a more modern tech without having to stall the feature roadmap. Ultimately, we end up shipping awesome stuff fast, which is always the goal. So thanks. Appreciate y'all listening. You can follow me on GitHub, Twitter, Instagram, LinkedIn at the Valosek. I want to give a shout out to Camille, Garrett, and Lisa over at Unomi for all the help with this presentation the last week or so. Shout out to Adam and Andrew over at BoltSource for putting GraphQL Texas together. And thank you all for tuning in. That's it. I believe now Q&A. So if anyone has any questions, I would be happy to answer.
Yeah, thanks a lot, Brandon. We'll, like Brandon said, we'll go ahead and kick off Q&A with him now.
Let's see. So is that there in the chat? Resolve runtime complexity. Is this really a cost compared to N+1 request between front-end and RESTful API? No, it shortcuts a lot of the problems. So the N+1 problem is probably the most hyped feature of embracing GraphQL from a client side. So that's specifically this idea of requesting information. Let's say I want the top 20 users in my friend list, but I also want their avatar and other image information. An N+1 request is if I have 20 of those users, a naive approach would make 20 requests to get that additional information. With GraphQL, from a client perspective, you can make that request in a really nice kind of nested way that looks very clean. The resolver complexity that I'm talking about, that is leveraging things like data loader, that is leveraging things like very aggressive batching, which is not caching, but batching requests together in order to make this in a sort of stagnated approach of querying these pieces of information in large volumes. So the N+1 problem, without getting too deep into the CS weeds, because I'm probably wrong on this, goes from like really like a big O of N problem where you're just scaling out for each of these additional pieces of information that you're requesting, and closer to like a log N type thing where you're able to rely on a more stagnated approach to requesting these pieces of data. The best thing, if you want to know what that looks like, is to Google data loader and really read into specifically the way you have to implement these batch methods and the way it allows you to write very simple looking resolver code that will result in really cleanly batched large requests. Can you explain how the Graph API gateway communicates with the microservices? Are services responding directly from the DB? How's that typically formatted? So that's going to depend on how you're building out your cloud, right? So I can speak for how I like to build stuff, which is heavily leaning on the serverless side of things. So the API gateway is exactly that in AWS. It is a serverless managed API gateway that can delegate down to serverless Lambda functions that can execute these requests. So just following the request through to kind of address the infrastructure along the ways, as a request comes into the API gateway, that's handled by the GraphQL Lambda resolver that receives the request, that's executing the Apollo code, that is basically parsing the query and firing off all these things. From there, you need to make these requests down to the microservices. Now, the way that looks for us at Unomi, the way I like to build that is that's still just an AWS making Lambda invokes those specific serverless functions, but it doesn't have to be that way. And like I was saying, real life platforms tend to be a Frankenstein's monster eventually. And so you're going to have a mix of transports when you're doing that. You could be making Lambda invokes. You could be calling a REST API. You could be calling a third-party REST API, or even reading directly from a database or a file. Even the graph smooths over all those differences, basically. Event-driven versus sync, gRPC, for example, are events necessary as primary transport or dependent on product requirements? For example, eventual versus immediate readability, profile update versus device telemetry submission. Event-driven is a very umbrella term overall for a lot of this. When I was talking about event-driven architecture specifically, I was talking about this idea of relying on events to have an eventually consistent model across your platform to sync information that's changed. So in that case, that's an implementation detail on the architecture of, I have service A over here that does something and it's going to announce that to the rest of the platform, that the rest of the platform can listen to that event and then update their own local data store basically to handle that. You also keyed into a specific thing of this is a product requirement versus like a implementation detail. That's also what I meant too on the graph as well. Like if you have a high volume data ingestion endpoints, that's going to have a different set of product requirements and expectations and response time and latency like that, versus say your more product level graph API that's serving your apps. Questions under the QA tab. I don't know how to get there. Can GraphQL be used between multiple databases? Yes. So GraphQL can, like your GraphQL gateway, the very top part of that request flow, that can connect directly to a database if you want. Especially if you're kind of dealing with some legacy stuff, maybe that makes sense. But in the diagrams that I was showing in this really distributed architecture, you're talking to individual microservices. And at that point, you don't care what database they use at all. You could have a relational database on one side, you could have Elasticsearch on another microservice. You choose the best tech for the job of what you're trying to solve on those microservices, and you rely on that. Now, you could totally talk to the database directly from your graph. But again, if you're going from this distributed approach, that level of coupling starts smashing a whole lot of stuff in that gateway level. I'm skeptical about the actual need for GraphQL. Okay. seems that the more thoughtful, more granular modeling and the bloated canonical model combined with traditional data caching, Redis, etc., or NoSQL document databases like Mongo to hold read-only composite entity data that's updated when events occur could do exactly what GraphQL does. Yes, you could reinvent GraphQL. You could take your own approach to doing a lot of this stuff, but one of the biggest advantages of GraphQL is the fact that it is a very thriving ecosystem. And it is a hugely batteries included paradigm overall. It is a runtime, it's a query language, it is a solution to building SDKs, it's a solution to building documentation, all this sort of stuff comes out of the box. Now, small platforms or things that aren't likely to scale or things that are working on seriously by just like a few people, this is going to be really, really heavy handed. I'm not talking about building out basic platforms like that. I'm talking about teams of engineers working on large scale distributed platforms that are able to do that. The best thing in my experience when it comes to architecting platforms is doing everything you can to firewall design decisions. What I mean by that is you have different teams working on different parts of the stack. At some point, someone may try to push conventions or some cross-cutting concerns of adopting a piece of technology. That's eventually going to be a bad decision unless it's just perfect and you're able to see the future. Stuff eventually will get brittle. Stuff eventually will feel non-ideal. The best thing we can do as architects and people designing platforms is to firewall these tech decisions the best we can. Adopting a single monolithic database means that the entirety of your platform is now operating with that set of assumptions, and that the details of that tend to leak throughout the platform. The worst example of this would be something like a traditional monolith where you have a very, very powerful active ORM style database driver, and every part of your code is calling ORM methods and hitting the database without anyone understanding what's going on. That's totally fine if you're a team or a person building an application, but at scale with different teams of engineers that come and go and trends and engineering culture that shifts over time, that is going to get very painful very quickly. What kind of caching paradigm is used by Apollo Federation? Great question. I have no idea how that works. Sorry. What are your thoughts on having ID be a foreign key versus each separate object having an explicit foreign key and its own unique ID? I'm not exactly sure what that means. So each object, each entity really has an ID that identifies it across the system. So different microservices, different parts of the platform, that is the single way that you can correlate that stuff around. What I like to call cross-service foreign keys, this would be something like your device service having a user ID. That doesn't mean anything to the device service. It is simply an opaque ID that it was handed and it's storing in association to the device. That pattern of having these cross-service foreign keys is super powerful and is exactly how you enable this ability to correlate information across entirely different parts of your application easily. For creating this composite entity, you were talking about you're using Apollo Federation server, and if so, can you recommend it? Really great question, Benjamin. Excellent question. Apollo Federation is an extremely compelling offering. For anyone who's not familiar, this is the idea of instead of having a singular gateway where all of your schema information about your graph lives, the graph schema itself is actually federated out to those individual microservices, meaning now your microservices have a say in the way that they're surfaced in the graph, which sounds cool and totally makes sense, especially if your teams get really large. But at the same time, you're foregoing a little bit of one of the greatest advantages of GraphQL, and that is basically forcing you on a technological and business and product level to acknowledge and define and explicitly state what is the surface area of my platform, what are the operations that I can do, and what does my data look like when I surface that. So you can. I think Apollo Federation stands to be extraordinarily sick, to be honest. But I would really want to play around with that a lot to understand exactly what some of the downstream ramifications of adopting that would look like and ensure that you don't end up kind of blowing stuff up long term. You mentioned that GraphQL resolvers can be compute heavy, particularly with Apollo clients. Can you elaborate on that? So yes, they can be compute heavy with Apollo server only because Apollo server is a beast. It's doing a lot of stuff. It is great. It is an incredible piece of tech. But you need to be very careful and instrument absolutely everything so that you understand exactly where your bottlenecks are. You can understand what the slow part of your requests are. Apollo comes with a ton of very cool instrumentation stuff just right out of the box. You can look at basically the stack trace to all of the parts of your cloud and the way that the requests are kind of cascaded together. And it is phenomenally useful. That being said, it is very beefy. So especially in something like a stateless environment like Lambdas or super short-lived containers or something like that, you have to be careful, and it's probably good to start caching certain things. Like here at Yonomi, on our graph server, we built dynamically the handler for Apollo. We had to make sure to cache that inside the Lambda execution context, because that's an expensive operation at first too, right? So just be aware of stuff. Don't over anticipate where it's going to be expensive. Just instrument it and just, pay down the slowness piece by piece. Can GraphQL be used with time series data? Yeah, sure. But it's one of those things where you may start looking at some data volume issues, especially if there's a whole lot of data transforms coming in through your graph server. This is where I think you can start suggesting that maybe this isn't something that belongs in the graph. There's a lot of cool approaches I've seen and even experimented with like creating your own views, basically. So you use the graph to provide query information and filter parameters and all this sort of stuff to build a view that you then get back an ID for, that you can make a traditional fully network cacheable GET request to large volumes of data. What's great about that is you're able to share these views around. They can benefit from all of the traditional, REST caching approaches and scalability approaches. And it allows you to offload all of that traffic off of your graph, because your graph request is going to be several magnitudes of 10 more expensive than a very simple GET request, and millions of times more expensive than a cached document on an edge somewhere on a CDN, right? Good question. Awesome. I think that's on time. So Adam and Andrew, if you want anything else. Oh, can GraphQL be used with HTTP2 based protocols? Great question. I hope so. That would be pretty sick. Awesome. Thanks, y'all. Appreciate it. Looking forward to the next speakers. And I think I'll hop in the Slack channel as well if anyone has any other questions. Otherwise, you can reach out to me on all my social channels.